Video for the second big idea. This one is all about explaining material properties. So using what we know from the first big idea about periodic trends and atomic behavior to explain chemical and physical properties of materials. So there's a couple concepts that fit under this idea. So we'd start with our different types of bonding and knowing the characteristics of ionic, covalent, and metallic bonds. Being able to distinguish a molecule as polar or nonpolar and knowing how that will affect its properties. Being able to determine what intermolecular forces act in a material. Being able to draw Lewis structures and pick out the correct Lewis structure based on its formal charge, and then being able to use that Lewis structure to determine the shape, the geometry of the molecule. And then we had the kinetic molecular theory, which can also be brought in to explain behavior. The special cases of gases that get a little more attention than the other two phases, and then finally properties of solutions. So let's take a look at each of those real quick. So remember, there were three basic types of chemical bonds with a couple typical characteristics. We had ionic bonds, which were composed of electrostatic attractions between a metal and a nonmetal, so charged ions being attracted by the opposite charges. Covalent bonds, which were distinguished by sharing electrons. These formed between two nonmetals. And metallic bonds, which naturally formed between two or more metals, which are distinguished by their sea of electrons, all of the electrons being shared between the metal atoms. And here are some examples of those bonds. And then we talked about being able to draw Lewis dot symbols, Lewis dot structures, and Lewis diagrams for both atoms and compounds. So you were pretty good at this. Here's some examples of just individual atoms. A quick reminder that when you're writing a Lewis structure, sometimes there's more than one configuration that you can draw it in. Sometimes there's more than one place you could put a double bond and still have the octet rules work out and the total number of electrons work out. And so to decide which one is correct, you assign a formal charge to each atom in the structure. To do that, for each atom, you count the electrons in lone pairs as one electron. So if there's two dots on an atom, that's two electrons. And then half of the electrons in bonds. So if an atom has one lone pair and one bond, it would look like there are 3 electrons around it. And you'll subtract that number from the number of valence electrons that that atom would have brought into the compound. And that's its formal charge. So here's an example. Here's 2 possible ways we could draw the Lewis structure for CO2. See, both of these include the right number of electrons. Both satisfy the octet rule for both elements. And so to figure out which one is better, we'll calculate their formal charge. So the valence electrons on the oxygens is 6, on carbon is 4. That just comes from the column they're in the periodic table. And then we're subtracting away the electrons that each sees. So this oxygen is 1, 2, 3, 4. Those each count as 1. And then 5, 6. It's seeing half the electrons in this bond. Over here, this oxygen has 1, 2, 3, 4, 5, 6, 7. And so we do that for each element, subtract that number, and so here are our 2 formal charge options. We want to pick the structure that minimizes formal charge. So this one is the preferred structure. If you can't get all the formal charges to be 0, remember that the preferred structure will be the one where the negative formal charge is on the most electronegative element. There were some exceptions to the octet rule that is important to keep in mind when drawing Lewis structures. there's 3 possible exceptions. We could have ions or molecules that have an odd number of electrons. Obviously, if there's 7 valence electrons to work with, you're not going to be able, well, if there's an odd, that's 7 special. If there's an odd number to work with, you're not going to be able to put an even number on each element. The math doesn't work there. If the ions or molecules have less than an octet, if they only brought in 6 or 7 electrons total, you can't form 8 electrons. They're not there. And finally, ions or molecules with more than 8 valence electrons. This was called an expanded octet. So things like SF6, where the sulfur is able to form 6 single bonds, even though that means it's seeing 12 electrons. Things that are in row 3 or lower are able to do that. They end up expanding into their d orbitals and placing extra electrons there. Once we had a Lewis structure, we could figure out geometries based on electron domain numbers. So remember, we picked out the central atom and figured out how many electron domains, how many groups or bubbles of electrons were around it. And that gave us a geometry. And these geometries are determined by the fact that those groups of electrons want to spread out as much as possible. So these are the geometries that let each group of electrons stay as far away as possible. Once we knew the electron domain geometry, or the number of electron domains, electron bubbles, we could figure out the molecular geometry by imagining the electron domain geometry and then replacing sites with lone pairs as necessary. So remember, for example, if we had 4 electron domains, we'd have the tetrahedral electron domain geometry. If all of those groups of electrons are single bonds, then we just have a tetrahedral molecular geometry. No problem. Remember that if one of them is a non-bonding pair, we wouldn't see this site when we looked at the molecule because it's an electron pair. It's not an atom. We can't see it. We would instead see the remaining atoms, and so we would describe this shape as trigonal pyramidal. So go ahead and just take a moment to look back over these possibilities. Keep the different names familiar in your head. You will, of course, be able to reference your notes on this year's AP exam, so this might be a good thing to have near you. All right, next came the concept of polarity, which arose when a molecule did not have an even distribution of electrons, when it doesn't share them evenly. And so this followed geometry because it's useful to look at the shape of the molecule first, because if it's symmetrical, like this example, we probably have a nonpolar bond. You see, it doesn't matter that electrons are more attracted to the oxygen than the carbon in this molecule, because it's a linear molecule. These two bond dipoles are going to cancel out. They're pulling in equal but opposite directions. If this was a tug of war, there'd be no movement on the central carbon atom because these are equal. By contrast, here we have oxygen. It also has polar bonds because of the electronegativity difference between these atoms. But in this case, the molecule is not symmetric. So if we were to think about combining these bond dipoles, they are overall pulling in the upwards direction. They're both pulling in opposite left and right direction, so there's no left or right motion on the oxygen, but they are both pulling it up. So the oxygen would feel, or the electrons rather, would feel a pull in the upwards direction here. So this molecule would be polar. There'd be a greater electron density on top of the molecule, making this side slightly negative, and a lack of electrons on this side, making it slightly positive. Remember, electronegativity increases diagonally to the right on the periodic table. And the more electronegative an an element is, the better it is at attracting electrons to itself. So the greater the electronegativity difference, the more polar the bond between two elements is going to be. A couple other properties of bonds. We briefly talked about the order of a bond. This doesn't come up too much, but if it does, it's not too difficult to figure out. It's just the number of bonding electron pairs shared by two atoms in the molecule. So the number of bonds. This can be, typically they are integers, but it is possible to have fractional values when we have resonance structures. Bond order is useful because bond strength increases with bond order. We know this intuitively if we think about it. If there are single bonds, those are weaker than double bonds, which are weaker than triple bonds. Bond length is inversely proportional to bond order. We know this as well. Single bonds are longer than double bonds, which are longer than triple bonds. Bond strength also increases with the difference in electronegativity between two atoms. So the bigger the electronegativity difference, the stronger the bond between those two atoms. All right. Remember that it takes energy to break these bonds. So the reason we care about bond strength is because it helps us figure out how strong that material is going to be on the macroscopic scale. The stronger the bonds are, for example, the higher the boiling point will be, because we have to input more energy to break those bonds. Well, yes, I suppose that'd be the higher the dissociation energy. And then going in the reverse, that same amount of energy is going to be released when the bonds are formed. So if more energy is released than is required to break the reactant bonds, the overall reaction is exothermic. Remember those charts we looked at with energy levels, seeing the overall energy change for a reaction? We have to put in energy to break our reactant bonds, and then we get energy out when new bonds are formed. And so we could calculate delta H by taking the total energy of the bonds in our products minus the total energy of the bonds in our reactants to see how the energy changed for that reaction. If more energy was required to break bonds in the reactant, then the energy supplied, that the energy we got out by forming the bonds, we'd have an endothermic reaction there. So we had this main equation in our thermodynamics section that we used, finding the delta H for any reaction. We can go to tabulated values and sum up the bonds that were broken. So, my mistake, the bonds in our reactants. So the total bond energy of the reactants minus the bonds formed, the total energy in the bonds in our products. Bonds broken minus bonds formed. Oh, quick note, it might also be useful to have your textbook next to you when you take the exam, so you can quickly get to those reference charts in the back of the book that had all this thermodynamic data. We also needed to understand hybrid orbitals so we could make sense of those molecular geometries we talked about earlier. And again, this was just an extension of the chart we had made in our notes. If we knew the electron domain geometry, there was a hybridization state that coordinated exactly with it. So for example, if there were two electron domains, our hybrid orbital was sp. We've got an s orbital and a p orbital hybridizing together. If there were three electron domains, we had sp2. Remember that these superscripts on these orbital notations always add up to the total number of electron domains. So 1s plus 1p orbital hybridized to give us 2 equal energy hybrid sp orbitals. 1s orbital and 2p orbitals combine to give us 3 total hybrid orbitals, and so on. We then had a quick look at the two different types of bonds, sigma bonds and pi bonds. Sigma bonds were the end-to-end overlaps, and they always formed first, and only one copy of them was formed between any two sets of elements. When there were multiple bonds, everything after the first sigma bond was a pi bond, and those had the side-to-side overlap of typically unhybridized p orbitals. The main points to keep in mind for the kinetic molecular theory, if you need to use this theory to explain trends or properties, is that energy can be transferred between molecules during collisions, but the average kinetic energy will not change as long as the temperature does not change. So at a certain temperature, molecules have a certain average kinetic energy, and that average will remain the same. That's the main idea. If we increase temperature, we increase kinetic energy, we increase the average speed or the average energy of molecules. Talking about gases in particular, we built our ideal gas law from the four variables we needed to describe a gas: its pressure, volume, temperature, and moles. Remembering that under standard conditions, STP, which is 1 atm and room temperature, 1 mole of a gas occupies 22.4 liters. My mistake, this is actually 0 degrees Celsius in Kelvin. So in this example, all of these different gases with their different properties would all occupy the same volume at standard temperature and pressure. They have different masses, but as long as we have 1 mole of each, then we have the same volume, because our ideal gas law said PV equals nRT. If we are at the same pressure, the same temperature, and the same amount of moles, they must have the same volume. Here is our gas law. It's almost certainly going to come up, I would think. We can also modify it slightly to calculate the density of a gas. We know density is mass over volume, and we know that we could get mass over volume by rearranging the gas law. We know that mass is related to the moles of our gas. So we've got the pressure times the molar mass divided by the ideal gas constant times the temperature. Either of these formulas would give us the density. Remember that if we have multiple gases, Dalton's law of partial pressure says that the total pressure of the gas mixture is just the sum of the individual partial pressures of each gas in the mixture. His law looks like this. The total pressure is all the individual pressures added up. The presence of the other gases has no effect on the pressure of each individual gas, because when we talk about pressure, what we are really talking about is the motion of the molecules of that gas colliding with the walls of their container, and that will be unaffected by the presence of any other gases. The total pressure will only depend on the number of molecules of that gas. Here's a flow chart just to go through what possible routes you could take to solve a gas stoichiometry problem. So depending on which given information you start with, you can use different conversion factors to get to other pieces of information. So just to give you an example, if you started with the volume of a pure substance, let's say, you could use its density to convert to mass. You could use its molar mass out of the periodic table to convert to moles. Moles is sort of the big crossroads. Once you know the number of moles, you could convert to its concentration, its molarity, to use moles per volume to find the volume. You could convert between moles and number of particles with Avogadro's number, moles to mass with molar mass, or even moles of one substance to moles of another substance if we've got a chemical reaction between them and we know their stoichiometric relationship. All right, next up we had intermolecular forces. Remember, there were three main types of intermolecular forces, also known as van der Waals forces. We had dispersion forces, which were present in every material because they're just the result of the random motion of electrons. We had dipole-dipole forces that resulted between polar molecules because of the attraction between the slightly positive and slightly negative sides of molecules. And finally, we had the special case of dipole-dipole forces known as hydrogen bonding. They're similar to dipole-dipole forces. They do result in polar molecules, but they're a special case when the polar molecule is polar due to a hydrogen bond, due to a bond of hydrogen with one of the special very electronegative elements N, O, or F. So a hydrogen bonded to one of these three will be especially polar, and so it will have an especially strong intermolecular force. The other couple that we should keep in mind are if we have just ionic bonding, there will be ionic bonds between between the array of atoms in these materials. And we can have ion dipole forces as well. We know that ions have charges, polar molecules have partial charges, and so there can be an attraction between those as well. We also had phase changes and phase diagrams under this idea. So just a quick reminder of vocab here on the processes going between different phases. A quick note on vapor pressure, since this was a concept that was a little more difficult. Remember, the vapor pressure is the pressure that would exist in a closed container, the gas pressure that would exist in a closed container of a liquid. So you have a liquid, you put it in a closed container, some of it is going to evaporate until it reaches an equilibrium. And whatever pressure that evaporated gas applies to the walls of its container is its vapor pressure. So a high vapor pressure would indicate that a lot of the liquid evaporated. So it probably had fairly weak intermolecular forces if it was able to achieve that high vapor pressure. We could see that information graphed. So here we've got the vapor pressure of 4 different materials across different temperatures. So we can see at any given temperature, ethylene glycol has the lowest vapor pressure, and then water, ethanol, diethyl ether. So since this has the highest vapor pressure, a lot of it's able to evaporate. It definitely has the weakest intermolecular forces. We also need to be able to interpret phase diagrams when talking about phase changes. So a couple important things to remember. The gas phase will always be the one that occurs at high temperature and low pressure, because that's where gases would be favored. A very high temperature, a very low pressure, the molecules would want to spread out. The solid phase will be at the high pressures. If we condense material, we're going to push the molecules closer and closer together, making it a solid. And the low temperatures, because it would be freezing a material. The liquid will be in between. Along a line, the two phases are in equilibrium, and at this one specific point known as the triple point, all 3 phases are in equilibrium. The line between liquid and gas will end at a point called the critical point, because at temperatures and pressures above that, it becomes impossible to distinguish the liquid from the gas. A quick note on different ways to express concentration. Molarity is the most popular, and it's the one we spent the most time with. This is moles of solute per liter of solution. but it's also important to be able to know and use these couple of other concentrations. Molality was the most confusing, I think, because it sounds so similar to molarity. The important thing to remember about this one is it is over 1 kilogram of solvent. So it's still moles of solute, but now it's over a mass, and it's over the mass of just the solvent. So just the liquid that the solute's being dissolved in, as opposed to molarity, where we cared about the total volume of the mixed solution. In molality, we only care about the mass of the solvent. Mole fraction was moles of a certain substance over the total moles present. Mass percent would be the mass of the piece we care about over the total mass of the solution. Volume percent would be the same, volume of the piece we care about over the total volume. A quick note that sometimes you're asked for the mass percent of the solvent. So instead of taking the mass of the solute on top, it'd be the piece you care about, so the mass of the solvent. Alright, when we make a solution, we're going to have some sort of energy change. It'll either be endothermic or exothermic. If we are forming a solution, we'd start here, the solvent and the solute. There'd be some energy change. If we didn't know that, we could find it through Hess's law by going through the various steps required to form that solution. So first we need to separate the solute particles, so we need to break bonds, endothermic. Then we'd need to potentially separate the solvent particles, breaking more bonds, endothermic. But then, when the two separated particles are mixed and able to bond together and form new bonds, the formation of the new bonds will release some amount of energy, which would be exothermic, and the difference between the bonds broken and the bonds formed would be our total energy change for the process. Finally, we have the effect of temperature on solubility. We said that generally the solubility of solutes and liquid solvents increases with increasing temperature, and we can explain that in terms of the kinetic molecular theory, because at higher temperatures, particles have more kinetic energy, they're moving around faster, they're having more collisions, they're going to be able to dissolve more of a substance because they have more energy, they are in more motion, there's more mixing, they're better at dissolving that solute. Alright, let me go back all the way to that outline of ideas, just to make sure we got everything. Alright, so we can distinguish our different types of bonds. We can determine if a compound is polar based firstly on the electronegativity difference between the atoms. Secondly, if there is a polar bond we can look at the shape of the molecule to determine if it's symmetrical, in which case the bond dipole would cancel out, or non-symmetrical, in which case we have a polar bond. We can use intermolecular forces to describe properties of materials. We can draw Lewis structures to determine molecular geometries. We can use kinetic molecular theory to explain material properties. We can solve ideal gas problems. Oh, one other thing, it might come up in later big ideas. Make sure you can explain the important points of the ideal gas theory, what constitutes an ideal gas, and what the deviations would be from an ideal gas. Remember, the main ideas were that an ideal gas takes up negligible volume. The particles make up a negligible part of the volume of the gas, and that they have no intermolecular forces. So a gas in which we are very, very condensed, very pressurized, is going to deviate from ideal gas behavior, because if there's not a whole lot of volume, the particles themselves are taking up a greater fraction of the space, and so we're not fitting in with the ideal gas assumptions. And if the gas particles are having intermolecular forces, perhaps they're at a low enough temperature that they're moving slowly enough to start to interact with each other, they're going to deviate from ideal gas behavior because they're going to be slightly attracted to each other. Properties of solutions, we talked about the ways to measure concentration, talked about the effects of solubility, and then remember that being a solvent, having a solute dissolved in it, will have different properties. So remember, salt water, for example, boils at a higher temperature than pure water because the dissolved solute is interfering with the water molecules. It's holding them back, preventing them from evaporating at a lower temperature. The term from that was colligative properties. All right. Again, remember, hopefully all of the ideas mentioned here were familiar and ringed a bell. If one came up that made you think, oh, I kind of struggled with that on the first time around, I'm not sure I really understand it fully, that'd be a good one to go back and look at the original slides from that unit. You can try practice questions on it, you can look at the slides we covered, find other sources that talk about it, or email me with questions over it. All right, happy studying.